Let's try it one more time. So this was fun. This is a kind of a close analogy to the way... Hi, I'm Simon Whitmell. I'm an R&D engineer. Now, SpaceX has been in the news a fair bit recently with their trips to the ISS and the ongoing testing of their new rocket prototype. So I thought we'd go back and look at some viral videos of the Starship landing and talk about some of the control theory that goes into something like that. Let's take a look. Alright, so first we're going to look at a test flight of the Starship SN-10. Now this is a successful landing, and you can see from the get-go this looks a lot different from what you might expect a landing of a rocket to look like. They're bringing it down sideways, which is counterintuitive because it's not very aerodynamic, but that's the whole point. By coming at the ground sideways, they're maximizing the drag on the rocket body and therefore minimizing the terminal velocity, the speed at which the rocket's going to be falling. Now, this has two sets of lift surfaces, these forward canards as well as these rear fins, and each of them, as you can see, are articulated. And then this is the really exciting part where it goes from horizontal to vertical. This is a really, really complex control problem, trying to take something and basically push the bottom of the rocket in underneath it while it's falling. This is comparable to, say, balancing a ruler on your hand, something that's very, very unstable like that. So let's go back and take a look at it as it's falling. Talking about these lift surfaces, you can think of the whole body of the rocket as rotating about its center of gravity, and the drag coming from these canards and these tail fins acts like an upward force on that body. So by changing the drag in the front and the back, they can actually cause it to rotate about various axes, and this allows them to adjust the glide path as the rocket returns to Earth. Now let's jump forward and talk about how it stands up again. Essentially what's happening is something called thrust vectoring. They're firing the rockets at an angle so that it applies a torque so that the whole rocket will rotate about its center. So here you see they get the fins out of the way to minimize drag, and then this is applying a force on the body going this direction, and then it swings around. You can see it has to counteract that and bring it back the other direction in order to bring it down to ground. Now, on top of the difficulty of all of the rocket's weight has to be balanced on this bottom jet, but also as they come to ground, they have to control not only the rotation of the rocket, but also its position laterally. So that's a very, very complex control problem. Now let's look at its predecessor, the SN-9, and see how that can go a little bit wrong. Here we can see the rocket coming in for landing, and it's going to start to do the maneuver of just tilting itself back up onto its end, but as you can see, it doesn't have proper control authority. One of the rockets is not functioning properly, and it actually overswings and can't bring it back. It can't stop the rotation, and that's what causes it to crash into the ground. It's not able to get the rocket vertical in order to arrest its lateral movement, and the rotation continues until it crashes into the ground. So we've seen the SN-9 and SN-10 coming in for landing. Let's see if we can recreate those control problems using some benchtop equipment. All right. So this was fun. I took the pendulum and I got my 5-year-old to draw me a little rocket on there so you can see what we're doing. Now this is a more extreme example of what the rocket's doing. Here we have it completely upside down. And then through a series of motions, we're going to add more energy to the pendulum. We're causing it to swing higher and higher up. So this is something that they'd be doing with the rocket, using the fins, the tail fins and the canards to impart a rotation to the body of the rocket so we can get it standing up. Now, when it gets close to the top, when it's almost vertical, then you can start pushing, just nudging the bottom of the rocket left and right in order to get it underneath the center of gravity. You see, the center of gravity is way above where we can apply a force. So in order to balance it, you need to get it close to vertical and then be constantly pushing the bottom of the pendulum so it's underneath the center of gravity. And that's what's keeping the rocket vertical once it swings up and gets the rockets underneath it. And at that point, then it can start trying to control where it is left to right. And you can see if you push it, you give it a little bit of a disturbance, like either outside wind or another kind of force, and then colliding with the rocket. then you have to make an adjustment. We have to shift the base over so that the rocket stays in the center. Any shift left and right is analogous to the rocket drifting off of its intended path. All right, so this is our second experiment, and this is an aerospace platform. So it's got two thrusters that are offset left and right to the center of gravity. Now I've had my 5-year-old draw me a little rocket here so you can see, again, this is a system where the center of gravity is, I've added some weight above and slightly off center of the system to create sort of a difficult control problem where it's unstable or marginally stable, and the weight is not centered. So we have to try and apply differential force left and right. You'll see these two thrusters, they're actually working against each other when it comes to rotation. Both of them are pushing down, which is now the force which is slowing down the rocket. Because the weight is off center, differing the force between those two thrusters allows us to cause rotation in the rocket. And so again, this is similar to what we saw with the pendulum, where we're pushing left and right to keep the center of gravity over the point of force application. Here we're now applying actual direct torques by differing the force left and right. And as you can see, it can balance itself close to vertical, but as soon as it gets too far away from center, it has a lot more trouble. It takes a lot longer for it to get back to center. And any time spent at an angle here is analogous to the rocket drifting off of its course. And so you need to keep it really close to center, or else the rocket won't end up where it needs to when it gets to the ground. Now here's another, a slightly modified version of this, where I have taken the center of gravity and moved it up. So now the system is even more unstable. And this is actually a lot closer to how the rocket works. The center of gravity is really high compared to where they're applying the force. All of the weight in the rocket is much higher up than where the rockets are at the very bottom. So here you can see it's a lot more unstable. And if it gets more than a few degrees, maybe 10 or 15 degrees out of away from vertical, it starts to have real trouble returning to its center position. And here you can see if there's even a slight disturbance in this system, if it doesn't have enough control authority to be able to push back, then it will actually tip right over. And that's what we see happen to the actual rocket during the landing, is that it can't get the bottom of the rocket back underneath it. It can't get itself vertical in time to have a safe landing. So I hope that gave you a little bit of a better understanding of the control problem that's involved in landing a rocket like this. I mean, you're not going to assume that it's an easy task, but it might actually be even more complicated than you think. If you enjoyed this video, maybe give us a shout. Let us know what kinds of videos you'd like us to look at, and explain the science and physics behind it and some of the control systems that are used.